Okay, welcome back to our next lecture. We're going to start where we left off with yet another gas law. This one we won't spend too much time on, but this one is Avogadro's law. You may remember that name from Avogadro's number, 6.022 times 10 to the 23rd particles per mole. In fact, it was part of his work with gases discovering Avogadro's law that led to him discovering Avogadro's number. You'll see in a bit that they are very closely tied together. In conceptual terms, aka not math, Avogadro's law is really simple. More gas means more volume. Duh. When you have plenty of gas, the more gas you have, the more volume it takes up. I mean, that's just, matter is anything that has mass and takes up space, so more gas means more volume. But the less obvious thing is that the same moles of different gases will have the same volume. To put it in terms more like the other gas laws we looked at, Avogadro's law is saying that at constant pressure and constant temperature, if you increase the moles of gas, you have to increase the volume they'll take up. You decrease the moles of gas, you decrease the volume they take up. But if you have the same number of moles, you'll take up the same volume. And this is regardless of what kind of gas you are talking about. This is one of those things that helped confirm atomic theory. Now remember, Avogadro was working at a time when atomic theory was dangerously new. It was avant-garde, right? About the same time as John Dalton. So these two were sort of confirming one another's work. What helped Avogadro determine that moles, particles, atoms were real, and that Avogadro's number was the way to look at things, was that he discovered that at what we now call STP, or 1 STP, that is to say at 1 atmosphere of pressure and 0 degrees Celsius, 1 mole of gas, of any gas, will take up 22.4 liters of space. Okay, so 22 and a half liters, that's about 11 and a quarter 2-liter bottles of soda. So it's a pretty significant amount of space, especially when you consider you're talking about 2 grams of hydrogen. at 1 atmosphere of pressure and freezing temperatures, that's a big volume. And it's also 32 grams of oxygen, or 254 grams of iodine. The same volume for these wildly different masses, because he's the one who realized you need to focus on moles. That was one of the things that led him to do that. So now let us leave Avogadro's law behind. I don't really want to do too much math with that. Let's just go straight on to the combined gas law. The combined gas law is pretty much exactly what you would expect it to be. It's a combination of the gas laws. You put together pressure and volume and temperature and moles, and it lets you predict what the system will do if you change any 1 or 2 or 3 of those. It's just saying that PV over NT is equal to a constant for any particular sample of gas. It's not necessarily immediately obvious how they came up with that, so I'm just going to briefly recap how they got there. You just have these 3 gas laws that we already covered, Boyle and Charles and Avogadro. PV is a constant, V over T is a constant, V over N is a constant. Well, somebody put that together with the realization that an unnamed gas law is very similar to the Charles's law, or Gay-Lussac's law, namely that pressure over temperature is a constant. If you increase the temperature of a vessel, of a gas inside of a sealed container, pressure will go up until the container goes boom. And then they combined that with the other laws to come up with an early version of the combined gas law. PV over T is equal to a constant. Then they looked at Avogadro's law and said, hey, those are similar as well. PV is a constant and T would be a constant too, if you held your sample at constant pressure and constant volume. So they went ahead and combined all their gas laws into a single gas law. PV over NT is equal to a constant, or P1V1 over N1T1 equals P2V2 or N2T2. Take a sample of gas, you fiddle with it, and things are going to have to change, and you can predict how they'll change. Once again, I don't really care too much about the math on the combined gas law. Not because the math is particularly difficult. It's not. It's the same sort of algebra we've been doing the whole time. But because the combined gas law is nowhere near as interesting as the next step in our little study of gases, the way things work, and namely the ideal gas law. Because when you look at it, pressure, volume, temperature, and moles are really everything there is to know about a sample of gas. There's not really much else you can measure about that wouldn't be in some way tied to those four factors, which means that the constant that we're looking at for the combined gas law, PV over NT equals a constant, that is a really, really important constant, and it is going to be in some way very, very important to our study of chemistry moving forward. So I'm going to go ahead and leave it here. Just know that instead of memorizing all those other laws, it might be easier just to memorize the combined gas law, PV over NT equals a constant. And from that, you can derive the other laws. Just say, what happens if you hold two of these constant? If you hold moles and temperature constant, you're looking at PV equals PV. If you hold volume and moles constant, then it's P over T equals P over T. The unnamed gas law that we didn't really talk about. V over N, B over N, NT, NT, if you're being kind of weird. So you can derive any sort of the gas laws just by looking at the combined gas law. Or if it works better for you the other way, memorizing people's names and things like that, then you can go ahead and memorize each of the gas laws and use them to get to the combined gas law. I don't necessarily recommend that you memorize any of the gas laws. I will be including all of the laws with the names of the dead white guys on the sheet at the end of the test. But understanding where the laws come from and what they mean, it might be helpful to you. I don't know. That's entirely up to you. Just remember, I will expect you to do some math with Boyle's law and Charles's law, or Gay-Lussac's law, less so with Avogadro's of the combined gas law. I will definitely be expecting you to do math with the next law, the ideal gas law. But I'm going to go ahead and save that for another lecture and pretend that our schedule didn't get completely messed up by torrential rain.